Example 4.8, moving a crate. We want to apply the second law of motion, acceleration equals sum of forces divided by the mass, for a system not in equilibrium, together with a kinematics equation. The combined weight of the crate and dolly in figure 4.17 is 300 newtons. If a man pulls on the rope with a constant force of 20 newtons, what is the acceleration of the system, crate plus dolly, and how far will it move in 2 seconds? Assume the system starts from rest and that there are no friction forces opposing the motion. To find the acceleration here, we will apply Newton's second law, which says acceleration equals the sum of the forces divided by the mass. Of course, this will involve the normal force, which is in the y direction, plus the force of gravity, which is in the is also in the y direction, plus the pull of the man who seems to be pulling horizontally in the x direction. The normal force and the gravitational force cancel out, so you get, because they are equal and opposite to each other, and we're just left with the force in the x direction. So basically, we need to find out what m is. M is going to be, according to this equation, m is w over g. So we can say acceleration equals f sub x divided by weight over g. And the mass turns out to be 30.6 kilograms, 300 newtons divided by 9.8 meters per second squared, newtons per kilogram. And the acceleration is 20 newtons over 30.6 kilograms, which is 0.653 meters per second squared. So I will put a square around that. And now we'll go back to one of our kinematics equations, which says that delta x is going to be 1/2 at squared, because we've got the time, we've got the acceleration, and we've got the initial velocity is 0. And so this will be 1/2 times our acceleration of 0.653 meters per second squared times our time of 2 seconds squared, which is 1.31 meters. Question 4.8 is, what effect does doubling the weight have on the acceleration and the displacement? We had calculated that delta x equals 1/2 at squared, and that the acceleration was equal to the force times gravity over the weight, so that would mean that delta x was equal to f sub x times g over 2w times delta t squared. So doubling the weight would half the distance that it was traveled. Example 4.9 is very similar to example 4.7, except we don't have any tension in this rope. We've cut the rope and the car is sliding down the hill. We have a car of mass m is on an icy driveway inclined at an angle of theta equals 20.0 degrees. Determine the acceleration of the car, assuming that the incline is frictionless. If the length of the driveway is 25 meters and the car starts from rest at the top, how long does it take to travel to the bottom? In part C, what is the car's speed at the bottom? So once again, I'm going to draw this triangle that is related to mass times gravity. It's the weight of the car acting downward, and we're going to divide that into two components. the normal component and the parallel component. The angle here, for reasons I've stated before, is the same as the angle here. So the parallel component is mg sine of theta. This is a right angle. And the normal component is mg cosine theta. And the reason is because this is the side adjacent, so it's related to the cosine, and this is the side opposite, so it's related to the sine. Now the force of gravity in the normal direction is exactly canceled out by the normal force. But the force of gravity in the parallel direction, we used to have a tension up here holding that sled in place, but now we don't have any tension in place. So we're going to say that the acceleration is equal to that parallel part of the gravity divided by the mass of the car. And you can see why they didn't bother to tell us the mass of the car, because these two things cancel out, and we'll have the acceleration is just g sine theta. So plugging g in is 9.8 and theta is 20 degrees. We get 3.35 meters per second squared as our acceleration. Now we can use the methods that we've used before. We had a zero initial velocity, a delta x of 25 meters, a time unknown, acceleration of 3.35, and then we should be able to solve for the velocity and time. So you can work out this as you like. We got a final velocity of 12.9 meters per second, delta t of 3.86 seconds, and our acceleration of 3.35 meters per second squared.